Okay, thanks for coming to our weekly seminar. We only have a few left. Just a reminder that we'll do this till the end of the semester, so if you haven't done it or haven't heard that you're supposed to do it, you should check with Tracia or your advisor to make sure you're not on the list next week. This week, Armin's going to present on some work he's been doing over the last couple of years regarding the disc compact tension for concrete. And he'll explain a little bit about that. Armin's been here now almost 3 years and came from University of Clemson, or is it
Clemson University.
I almost said South Carolina University. That would
no.
be good. So he's going to finish his thesis up here in a couple weeks, hopefully.
Okay, so yeah, we're going to talk about the DCT test for concrete. This test has already been a standard for asphalt, and we decided to use this and see if we could get more properties out of it. So we wanted to get fracture properties out of this test rather than just one single parameter of total fracture energy. And I like fracture because it gets me all cracked up. So yeah.
Yep.
So essentially, fracture is the process of creating traction-free surfaces, not creating horrible movies with Anthony Hopkins in it. Was it a good one?
Yes.
I didn't see it, actually. It got a horrible rating online, so I just assumed it was bad. So we want to be able to describe the traction-free creation and be able to do it accurately so we can predict the pavement performance. And there's essentially 3 types of fracture. There's mode 1, and this is preferred. And by preferred, I mean it's the easiest mode to induce, and it's the mode of least resistance. So cracks that start in other modes will actually transition to mode 1 given enough time and fracture length. And then we have mode 2 and mode 3, which is just shearing and tearing. These are not really common in pavements, which is what we were looking at, so we concentrated just on doing a simple mode 1 test. So why don't we just use strength to predict our slab capacities or predict how long a concrete structure will last? Well, you can't just simply take a structure if it has a crack in it and just take the surface area and divide it by the load to get a stress, because you have these stress concentrations at these crack tips. And these stresses, theoretically, go to infinity as you get exactly at the crack tip. So there's a singularity there. And we need a way to calculate how much stress is actually at this crack tip as opposed to throughout the entire structure, so that we can predict if the crack will go forward, will it start, and how strong the actual concrete pavement in this case would be. So there's a couple ways to go about this. One way, which we're not going to talk about, but there's been lots of research into, is using something called the J integral. And this essentially describes a sort of a fracture energy surface, and you're taking integrals and derivatives of everything. And this technique is wonderful when you have multiple specimens with different notch lengths to test. So this gives you really consistent and accurate predictions, but you need a lot of specimens to test using this to get a very accurate value of J. So instead, we're going to look at a stress intensity factor, which is somewhat simpler because there's only a couple terms in the equation. I don't have a laser pointer. That's fine. I can walk in front of this. Okay. So this is the applied stress. This is pi. That's constant, so that makes it easy. This is the essentially defect length. And this is a geometric correction factor for the geometry of the structure you have. So that is usually what changes depending on what type of test you're doing to measure this. And you calculate all that, and you get a K value. And this 1 right here signifies that it's a mode 1 K value. You can have a mode 2 and a mode 3, depending on what your test induces. But we're just going to worry about mode 1. So using this idea of a stress intensity factor, there is a couple limitations. We can't calculate stresses right at the crack tip or very near the crack tip because the idea of a stress intensity factor is not really valid. There's a lot of nonlinearity there. In concrete, there's a fracture process zone where these micro cracks are beginning to form. And so our idea of K is not entirely valid very close to the crack tip. However, there's a nice region around the crack tip where it is valid, and knowing that will give us a very accurate prediction of the behavior of the specimen. And before we go ahead, we like to simplify a lot of things, and so we're assuming with this DCT test that our concrete is linear elastic, it's homogeneous, it's isotropic, and we're only in a plane stress state. These are not all true. However, we're trying to see just how rigorous we need to be with this. Linear elasticity is it's pretty close depending on the load level. As you get to near the peak load, you get some nonlinear effects, which we'll talk about later. Homogeneous, well, concrete has aggregate particles in it, so it's not entirely homogeneous. However, it does behave more like a composite material than, well, you would think, I guess. And it's fairly isotropic, and we are pretty sure we're inducing plane stress because our specimen thickness is a lot less than our specimen fracture length. So with this K value, we can quantitatively calculate when a crack will begin at or if a crack will begin at a given stress level. And this is huge because if we have a concrete pavement, we can accurately determine how much stress is being applied to that pavement depending on what kind of vehicle is going over it. And if we know what our critical K1 value is, we calculate the given stress level. If that K1 is less than our critical, well, theoretically the pavement's not going to crack. So this is huge for determining or calculating pavement performance. Now we come into a problem when we're trying to measure that critical value because for large specimens, it's easy. For small specimens, it's pretty hard because you have size effect issues over a shorter range. Like in a small specimen, it's not entirely homogeneous, so the heterogeneity comes out. And we have nonlinear effects near the peak load, which you'll see later in the presentation. So there are some issues using these small specimens. And what do I mean by small? Well, that's kind of ambiguous. There's usually a lot of empirical ratios that researchers have come up with to determine what's essentially an infinite size specimen. And for the DCT, there's not really a good feel on that. Some researchers have tested 3 meter by 3 meter compact tension tests of concrete. I don't know how they did that, but they did that, and they got very nice results that showed that the K1 value is a material property and not a geometric property. However, once we go to these smaller specimens, it does become influenced by the geometry, but we have correction factors to account for that. And like I mentioned before, we need to be able to predict the pavement performance because right now we're slowly transitioning more to a mechanistic design, but the design was based on just flexural strength of a test beam. And that's sort of what this is showing. So a stress ratio of 1 is essentially saying that the beam to slab is the same. Like the load applied to the slab is the same as what the beam predicted. However, some slabs held 2.5 times more than what the beam would actually predict. And you can see that it gets, and this is a fatigue test, but there's a huge discrepancy between just a simple flexural strength value and the actual performance of a pavement. So we need something better to quantify how this pavement's performing and whether or not it's going to crack and fail at a given stress level. So right now, for concrete, there's actually a very nice test that's already been developed. It's in a RILEM standard, and it's a single-edge notch beam. You simply apply a load at the top middle. You have a notch here. You have a strain clip gauge at the bottom of the notch, and you're measuring the crack mouth opening. And from that, you can calculate a loading and unloading compliance. So we're graphing load versus that crack mouth opening. The first 50% of that initial loading is what we're going to call our initial compliance. And then we load until we get to a peak load, and then we unload it in a controlled manner. So this test requires a closed loop hydraulic system usually. And from this unloading curve, we get to unloading compliance. And then we can reload the specimen to failure so we can get a total fracture energy. However, to calculate K1 or K1C, we only need these loading and unloading compliances. The rest of the curve is not important. So the idea that we're going to use is that during that loading and unloading, the elastic modulus, which is here, doesn't change. So we have a general equation just for elastic modulus. This is the span of the beam, so that's constant. This is the initial length of the notch. This is a geometric correction factor for the beam, and that alpha is the ratio of the initial notch to the full fracture ligament. And this is compliance, depth, and width. So the only things that are going to change are the notch length, and by virtue of that, the value out of this geometric correction factor will change, and the compliances change. But we're going to assume that the elastic modulus stays the same, and in that way, we're going to set these equations equal to each other. And when we rearrange and cancel things out, we come up with this. So we know the unloading compliance. We know the loading compliance. We know the initial notch that we cut. It's very easy to measure. And we can plug that value into here using our ratio of initial notch to full depth, plug it into that correction factor, and we get some value on the right-hand side. And this value has to equal that. So we can just iterate until we find essentially that critical crack extension that gives us the same thing on the right-hand side. And when we do that, we now have a critical crack extension, and we can plug into this semi-complicated looking K function here, which accounts for the peak load of the specimen or the applied stress. It gets converted into a stress over there. And because this beam is only simply supported, we have to account for the actual weight of the beam also. So this value right here is accounting for that. And we have the span, we have pi, we have our now critical crack extension, and then we have the F geometric correction factor using that critical crack extension value. And when we calculate all that, we get nice values. And here's an actual test run. So we load it till we see that the peak has been reached. The standard says you unload it at 95% of this peak value. Sometimes that's difficult to see based on if it drops suddenly or it's kind of softening out, and we'll talk about that a little later because that can influence the results. This blue line here is what the calculated initial compliance is. It's taken from 0 to 50% of the peak load to ignore the effects of any plastic deformation that may occur near the peak load. And then we have our unloading compliance, which goes along the unloading curve. And from that, we get our data. So these are actual test runs. The average K1C value for these beams, which were tested at around 600 days, so this is really old concrete, was 2.2. To give you an idea of just where this is in the range of materials, Okay, yes. Silicon carbide is around 3, if any of you know what that is. Or steel can go anywhere from 50 to 100. And essentially, the higher the K1 value, the more energy or more work it takes to initiate a crack. So it means that the material is more ductile. So the lower this value, essentially it's saying that the material behaves, at least in terms of the initial crack, more brittle. And we have a limestone mix and a recycled concrete aggregate mix. And there's definitely a difference here. And actually the COVs, even though there's only 2 values here, are fairly low. They're reasonable for this type of test. There have been numerous papers to determine the statistical validity of these values, and came out that these COVs are perfectly okay. The GF is essentially the total fracture energy, which is how much energy it takes per unit length to continue that crack growing. So K1 gives you the point at which a crack initiates. The G sub F gives you the value of how much it takes to continue that crack. And so these are roughly the same values, and one of the reasons we think probably these are similar is because this concrete is so old. It was cured, wet cured for about 200 days and then tested at 600 days. So if we tested this at 7 days, 14, 28 days, we would see a much larger difference between these values. And then this value right here is the critical crack extension. The beam has a nominal or an initial notch of 50 millimeters. So that's saying that for the recycled concrete aggregate, roughly there's an 8 millimeter crack extension at the peak load, and for the limestone there's a 17 millimeter crack extension. So we have a test that works. It gives us good values. There's lots of literature on it that says it's good, but beams are difficult to extract from the field. It's very hard to go out into the field and saw cut out a beam. It takes a lot of time, effort, money. It's a whole lot easier just to go take a core, a lot easier to repair the hole you made too, and try and test that. So we decided, well, let's try to get the DCT to use as a fracture test. And so we're going to use essentially the same process to calculate the fracture properties. We're going to load it and then unload it. We're going to calculate the compliances and then calculate the fracture properties. So this is just a general schematic of what the DCT looks like. I'm sure everyone here at some point has seen them sitting out in the high bays. This is the ASTM geometry for the asphalt specimen. And it works out nicely because asphalt people also use a 6-inch diameter gyratory, well, nominally 6-inch diameter gyratory, and we cast 6 by 12-inch concrete cylinders. So this geometry was perfect to use. Now we have slightly different correction factors. I never showed you the beam correction factors, but for this geometry we had to calculate through finite element analysis the geometric correction factors for this type of loading, and Daniel Spring, who's one of Paulino's students, did all this finite element stuff and came up with these equations. So if you have any question about these equations, talk to him. I have no idea how these values came about. So, but I know how to use them. We have our correction factor, and we again say that the elastic modulus stays the same because theoretically, elastic modulus is a material property. It shouldn't change. And when we do that and solve and put everything on one side, we have our correction factor, we have our unloading compliance, and our loading compliance. The reason this looks a little neater than the other one is, A, we don't have to worry about self-weight of the specimen. Because we're pulling it in tension, any weight of the specimen is already being read by the load cell. So there's no unaccounted for load on the specimen. With the single-edge notch beam, all the machine is doing is just pushing down. So the specimen itself is also providing, through its weight, a downward force that needs to be accounted for. So we do this. We solve through iterations, a simple solver, to find what our critical crack extension is. And then we plug in this much nicer looking formula, because again, we don't have to worry about the self-weight of the specimen or the span. Here's our correction factor. We plug in our critical crack extension value into the correction factor. We have our maximum stress, which is the stress of the peak load. When we calculate all that, we get a critical K1C. And here's just a plot of an actual run. I'm going to plot this versus the beam a little later, and you'll see some differences. But again, we calculate the initial compliance at 50% of the peak load to ignore any of this nonlinear effects. And then we get the unloading compliance and do our calculations. And this is what we get. Now, this limestone mix and RCA mix is the exact same as the beams that I showed you earlier. And I'll have a table that shows both of them together. And these were also tested at around 600 days and were cured in the same manner. And as I said, I'll show you the two together. But the COVs generally go up a little. One possible reason could be because this is a smaller specimen than the beam. And so maybe we're introducing more size effect issues into it. However, the COVs are still in the range of a valid test, so it appears that it still can calculate these values accurately. And again, we saw that the limestone had a higher K1C than the RCA. The fracture energies are similar, but the limestone is a little higher. And for this geometry, our initial notch length is 27.5 millimeters. So the limestone had about a 10 millimeter crack extension, while the RCA had about an 8 millimeter or 9 millimeter crack extension. Now, the idea was to come up with a test that's equivalent to the beam test. And it didn't quite work out like we thought or were hoping for. When we compare the beam and the DCT data, then the number in parentheses is the COV. The fracture energies are statistically the same. We just ran a simple t-test to see if the values were equal. So for both the RCA and limestone mixes, for both geometries, the fracture energies were the same. But when we went to compare the K1Cs, we found that neither mix had a equivalent K1C value. And it's fairly obvious just looking at the values that they're not equal. So we were trying to figure out what went wrong, what could possibly explain this. There's lots of ideas we have floating around. It would have been nice had this worked immediately. It would have made my thesis a lot easier. But it does shed some light into the geometric effects of these tests and even the COV of the test, because it was interesting how for almost every property the DCT value had a higher COV. And the one idea we're leaning towards is that we noticed that when we plotted the DCT data versus the beam data, we had a much larger area of a plastic deformation or crack extension occurring in the DCT rather than the beam. And remember, these two mixes are identical. They were cast on the same day from the same truck, cured in exactly the same manner, and tested at around 600 days. So there's no age issue or mix issue with this. We're thinking that possibly this larger plastic deformation nonlinear effect could be causing those lower K1C values, because it appears that there's more of a crack extension in there that we may not be capturing, just because it's difficult with this test and the loading rate we have to use to be able to immediately unload this specimen. The loading rate for the beam and DCT is the same. However, the DCT reaches its peak load much quicker, probably by virtue of how it's loaded and the geometry. So we've tried slowing down the load, or I've tried slowing down the load, and what that results in is a test that sometimes malfunctions because the load or the rate is now so slow that the machine is having trouble even keeping up with it because it's at the bottom limit of the strain gauge resolution. And so some noise issues crop up and doesn't work out as well. So right now, we have figured out that, well, the fracture energy of both these tests appear to be equal, which is good because fracture energy is a sort of a unit value. It's per a unit length. So it's good that both the beam and the DCT can normalize to the same value. However, the K1C values are not, and one reason we are thinking is that there's more plastic deformation occurring in the DCT specimen before unloading, and that would lead to lower K1C values, which we see in our results. And with that, hopefully you don't have too many questions because I'd have to get to class at 2 o'clock, but I'm more than welcome to answer some. Okay.
I have a question. Here, the CMOD is measuring the displacement in the line of load.
No.
Here.
Here? No. The loading line's right here. The CMOD is in this plane. It's about, what was the value? 25 millimeters away from the load line.
Yes, I mean, in general. But in general, the direction.
Oh, yeah.
And in the SEB, they are not in one direction. And you are applying the load vertically and you are measuring the CMOD like this.
Yeah.
So it may have some effect on.
Yeah, that.
I mean, that you are seeing maybe it is due to that reason.
Yeah, that's also because, yeah, when you apply the load to the beam, there's more of a dispersion of the applied load and applied stress, which would lead to a, well, theoretically, a higher K1 value.
What if you measure the LLD in that beam test?
And the problem with that, if we take it directly from the LVDT of the actuator, there's stiffness issues in the actuator itself that would crop up in that data. We could try, I guess, to place like a neutral axis LVDT on there. I never thought about that. And see if...
People have done that.
Oh, people have done that? Okay. And they saw no major change.
Yeah, he brings up a good point, but as long as your equations account for the CMOD opening up, I'm not sure. It makes a difference in the K1C calculation. It wouldn't make a difference in the total fraction.
No. Yeah, the total fraction would be the same. But yeah, K1C, it could make a difference.
Actually, this point came in my mind because we have tested some SEB samples and we have measured the such energy based on LLD displacement and also CMOD. So they are quite different. Around 1.7, 1.6 ratio different.
Oh.
So that's why I thought maybe.
Yeah, no, it's something, well, I haven't done, but apparently other people have done research into that. It's a possibility to look into.
Yeah, I think his point is valid, that the fracture energy would be slightly different, but not the K1C. Correct?
Well, yeah, I mean, theoretically, K1C is a material property.
Yeah,
but
I'm saying that the opening
yeah.
ratio of load and CMOD, so it won't be affected, but the total fracture energy would be affected by how you measure the displacement.
Yeah. Well, that's a good point. Any
Other questions?
Which equipment did you use to do the SEB?
There's equipment down in Newmark. They have a actuator system down there.
There is no issue of like changing opened and everything?
We looked into that because I ran the DCTs up here and then the beams down there.
Yeah.
Another Alex also ran his beams down there. His values he calculates seem very reasonable and very consistent. The DCT values I have are very consistent, and Nathan and everyone else who's been using it has also haven't noticed anything in terms of equipment issues, like a load cell may be out or something like that. So
Yeah, there's also some other issues you didn't talk about in terms of we did this with a different setup. How does geometry?
yeah, and also so the DCT that's in the ASTM standard has a much shorter initial notch length than the geometry we found in a fracture mechanics handbook. And when we tested that geometry, we also got similar results to this ASTM geometry, which seems to indicate at least that the machine is running okay. Our equations, the way we're calculating things, is the correct method. So we're looking now into maybe size effect, plastic deformation, something else to explain the discrepancy.
Final questions? Okay, thanks, Armin.
Yep.